Okay, with the problem solving about titrations, okay? And here the major thing that you have to remember is that before the equivalence, you choose the couple that is in excess, which is typically the analyte, whatever is already inside your beaker. And it is the reduction potential for that couple. Even if that couple is undergoing oxidation, you use the reduction potential plus the Nernst equation to get the E of the solution. And it's that E of the solution that, determines the potential inside your titration or your graph. Okay, and again, in these titrations, we are not gonna bother with the reference electrode, okay? All you need to do is find this E of the solution. At equivalence point, however, when we have none of the reactants left over and their amount is equal to epsilon, then what you have to do is get a derivation of the equivalence point, the E at the equivalence point, which is simply number of electrons from the first couple times the E naught of the first couple plus number of electrons of the second couple times E naught of the second couple divided by the addition of the 2 electrons transferred for each couple separately. And after equivalence, you use the second electrode. Okay? Now number 27. Okay, we're going to titrate volume 20 milliliters of copper 2+ solution of concentration C1 by a selenium solution of concentration C2. And the concentration of the selenium is 0.1 molar. Write the equation of the titration, calculate the equilibrium constant, and there's a part B of the question, and that is to get the E at different volumes of selenium added. And they give us the E naught for the selenium couple and the E naught for the copper couple. Let's start off. The first thing that you notice is that there's a mistake in the question and that the question should read copper plus and not copper 2+. So correct that. The reason is, let's go back to the couples here. Look at the couples. I cannot have an oxidant reacting with an oxidant, okay? An oxidant has to react with a reductant. Clear? Okay. First, we're going to write the titration reaction, and if we automatically know the reactants, which is selenium 4+ reacting with copper plus, that means automatically the reaction is dictated to us by what is given in the titration. So we have to have on the reactant side selenium 4+ and copper plus. And in a titration, we just hope that when they add an oxidant and a reductant, that they're adding them in a way and in concentrations to get definitely a spontaneous reaction. Now, indeed, if we look at the E naught for the couple selenium and the copper couple, indeed, we have a spontaneous reaction between the selenium 4+ and the copper plus. The global reaction, add the 2 equations, and you're done. And the first part is, after we have the global equation, calculate the equilibrium constant. Well, you know by now that log K equals N delta E naught divided by 0.592, and therefore simple substitution, the number of electrons transferred for both as a combination is 1 times 1, which is 1. And delta E naught is E naught of the reduction half reaction minus E naught of the oxidation half reaction divided by 0.592. Get the K, and you notice that this K is fairly high, and thus the reaction is complete. And because it's a 1:1:1, this is definitely greater than 10 to the 6, and it is a complete reaction. We could also conclude that since the delta E naught is greater than 0.25, which if you calculate it, it is, in a 1-to-1, 1-1, we can get a complete reaction. Second part, calculate the E for volume of CE added, and they gave us different volumes. We're going to first look at the volumes before the equivalence point, okay, which is volume 10, 20, and 30, because if we calculate the volume at equivalence, let's do that. We know that the number of moles of the first couple C1V1 should equal to the moles in the of the oxidant, and reductants have to equal to each other, so C2V2 at equivalence. Okay, so solve for V2 at equivalence, and we have the concentration of my copper, the volume of the copper divided by the concentration of the selenium, which is added, and therefore my volume at equivalence is simply 40 mils. So all these volumes up to 30 milliliters are points before equivalence. So we have our net equation, and C2V2 and C1V1, when they're equal to each other, that is my volume at equivalence, which we just, that is my equivalence point, which we just got a calculation at the volume of equivalence. Notice sometimes I use equivalence point EP, or as the French, they call it EQ, either or is fine. So equivalence, EQ is fine too. So before the equivalence, who do I have in excess? Yes, it's my analyte that's in excess. So it's the copper, which is in the beaker, that's in excess. And it happens that that's also my reducing agent. Of course, we already calculated the K, which we said it's a complete reaction. So if the reaction proceeds and it achieves equilibrium, it goes pretty much advanced greatly in the forward direction, such that in the end, by the end of the reaction, we have 0 selenium 4+, which is my limiting reagent. I have some leftover copper 2+, which is C1V1 minus the limiting amount, C2V2, and the product is simply going to be C2V2 and C2V2 on the other side. Great. Of course, there's no such thing as 0. We could always go ahead and get the selenium as epsilon from the K. So what do we want? Yes, we want the E, okay, the potential of the solution, okay, on this half reaction, right? Because remember, it's all relative to the electrode, but in titration, all we really care is the potential of the solution. Okay, so even though my copper undergoes oxidation, since it is the one left over in excess, thus I have the both species, copper plus and copper 2+, and at equilibrium, as we already discussed in the lecture, at equilibrium, I can get the E of the solution from either couple, from the selenium couple or the copper couple, and it's easier to get it from the copper couple because he's the one left over. And thus, E of my solution will be E of my copper couple, E naught of the copper couple plus 0.0592 log divided by the number of electrons transferred, which is 1, log of, and notice there's a plus sign here, not minus, so plus means ox divided by the reduced form, just like in the couple form. So the oxidized form is this copper 2+, so that's C2V2, divided by the reduced form, which is copper plus, which is this expression. So let's substitute. So that's my general formula. At volume equals 10 mils, what do? Simple substitution. You have the E naught, and you have the 0.592 log. C2 is 0.1 molar. V2, the volume added of the selenium, is 10, so that's times 10. C1V1 is 0.2 times 20. minus C2V2, which is 0.1 times 10. Do the number crunching and you get this voltage for the E of my solution. At 20 milliliters, let's try that. So instead, everything else stays the same except the V2, okay? So substitute everything instead of the V2 and you get a potential. And guess what? What is 20 mils? Yes, that's half equivalence. And in a titration like this, what's half equivalence? Yes, that's exactly the E node of my analyte, which is the E node of my copper, in this case, copper couple. At V3, which is 30 mils, again, I'm still before equivalence, so I'm going to use this expression all the way through. Don't memorize this expression, guys. You should put everything into a chart form because you never know who's added to who, okay? If it's oxidant, reductant, so just use the chart. And so here, again, the only difference is the volume V2, put it in, and just notice that the E's are increasing as I'm adding selenium, okay? So the E's are increasing. So if I'm putting up a graph, the graph starts off low and starts to increase. Next part is volume equals 40 mils. Again, we're still right at equivalence now. We already did the solution for this. So if I'm at equivalence, what do we have? C2V2, C1V1. That's my initial concentration. And at equivalence, both of them run out, right? They become 0, 0. In a one-to-one, this is very easy because in a one-to-one equation, that's simply epsilon and epsilon. And therefore, I could either use C2V2 or I could use C1V1 for the product concentration. Again, these are not concentrations, these are moles or millimoles. But if you need concentration, you could use it. Just as a pointer here, I'm gonna go back. Notice here, I used only moles divided by moles or millimoles divided by millimoles. The reason is because if you take total volume, divide by total volume, the volumes actually cancel out. So you really do not need the total volume in this expression. At equivalence point, what do we have? We have both the copper and the selenium concentration is equal to epsilon, and I can go ahead, get epsilon from K and then use the E for either couple, or there's a derivation, which I'm not gonna go through because I want you to memorize this, okay? There's no need. And that derivation comes about by adding the reduction potential of both couples, okay? And then you get that the E at the equivalence point is N1 E node of the first couple plus N2, the number of electrons transferred in the second couple, E node of the second couple, N1 plus N2, where N is the number of electrons for each couple. And thus, we know it's a one-to-one and that the reduction potential, they both have one electron transfer, so N1 is 1 and N2 is 1. You have the E node of both couples, substitute in, and N1 plus N2 is simply equal to 2. Solve, and you get E at equivalence. The longer way would be to use K and find epsilon, then use either couple to get the E of the solution at equivalence if they ask for that. Okay, so after equivalence. So when we have now a volume added of selenium, which is 45 mils, we still have the same equation, of course. And so we're definitely after equivalence because I'm beyond 40 milliliters. And therefore, in this case, after equivalence, it's whatever material titrant that I'm adding, that's going to be my excess reagent. Of course, your number crunching C2V2 will tell you that that's going to be my excess if you actually sit there and multiply it. And so now what are we going to do? C2, V2, C1, V1, who's the limiting? Yes, the copper is now limiting. So copper is going to tend to 0, and that's my limiting amount. So that's going to be my X reacted amount. So that's going to be C2, V2 minus C1, V1, and this is going to be the limiting concentration, which is C1, V1. Same with the product. And now, if I want E of my solution, what do I use? Yes, I use my selenium couple because that's whatever I have both ions left in solution. And so E of my solution would be E of my selenium couple, which is equal to the E naught selenium couple. Again, on an exam, guys, you really don't have to put selenium 4 plus, selenium 3 plus. I would just put selenium, and you don't have to write it as a couple. Plus 0.592 log of, again, there's a plus sign, so it's oxidant divided by reductant. So the oxidant form of the selenium is Ce4 plus, and the reduced form is a Ce3 plus. So it's going to be this expression, C2V2 minus C1V1 divided by C1V1. Again, each of them is divided by total volume, but again, as in acid, base, and Henderson equation, here the concentration is in the E is independent of concentration, and therefore, if independent of dilution, and if I add more water, it doesn't get affected because the total volume on top and bottom cancel. And now it's a simple substitution at 45 mils added for V2, substitute instead of V2, 45 milliliters. You have C1, you have C2, and you have the E naught. Get the E of my solution from the CE reduction potential. At 80 mils, again, substitution. What do you notice about 80 mils? This is a special value point, which is actually 2 times the V at equivalence point. And if you look at the overall potential that we get, okay, what is that? That's just simply the E naught of the selenium couple. So at 2V equivalence, we get the E naught of the selenium couple. And that's it for a 1-to-1 type titration. This is the only real thing that you really need to do. It's not as difficult, as the total explanation of the titration. So make sure that you understand this type of how to write out the chart, and simply using only one couple to get the E of my solution. And that's it. And memorize, again, memorize at equivalence, the equivalence point expression. I'm just going to go for it here. Where is it? Okay. There it is. Make sure you memorize this. Call it N1, E naught 1 plus N2, E naught 2 divided by N1 plus N2.